the school is Professor Kota Hattori from University of Keio. He will speak about spectral convergence of geometric quantization.
Thank you for the introduction. First of all, I'd like to thank the organizers for giving me the opportunity of the lectures. And I was looking forward to Germany, but I cannot do it. So please let me talk from Japan. So I'd like to use whiteboard. The title is Spectral Convergence in Geometric Quantization. And I have 4 sessions, and my talk is based on the joint work with Mayuko Yamashita at Kyoto University. Today, I will explain the fundamental notions of geometric quantization, and I explain the fundamental definitions and notions, the basic settings of my. First of all, let X and omega, we say the pair of X and omega, a symplectic manifold. If X is a smooth manifold of even dimension, whose dimension is 2n, and omega is a 2 form on X, which is non-degenerate, and closed. Then we call X and omega the symplectic manifold. Next, I define the notion of prequantum line bundle. LH nabla is called prequantum bundle. If L is a complex line bundle over X, and H is a Hermitian metric on L. Nabla is a Hermitian connection on the Hermitian line bundle L and H. Here, the connection is called Hermitian connection when nabla preserves H. So H is parallel with respect to nabla. And moreover, I suppose that, assume that form F nabla is the curvature form of nabla given by minus square root of -1 times omega. This F nabla is curvature form of nabla, so it is defined by. Now you and sorry, I have chat. F nabla UVS is U nabla VS minus nabla V nabla US minus nabla bracket of UVS. And this is the curvature form of nabla. Then if we have this assumption, then we call this triple LH nabla is called, we call this triple prequantum band on X and omega. Then if now let X and omega be a symplectic manifold, assume that omega over 2 pi is in the integer coefficients cohomology, then there exists a band such that the first chancellors of omega is given by omega over 2 pi. Now, the notion of geometric quantization is, this is my interpretation, is to define the good space of subspace V of the space of the section by using the additional geometric structure. Here, additional structure is called polarization. And in this talk, I consider two types of polarization. One is the complex structure. The polarization comes from complex structure. And the second one is, comes from Lagrangian fibration. So I'd like to explain these two types of additional structure. The first structure is complex structure. So complex structure means that J and an endomorphism of the tangent bundle of X, and the square of J is -1, minus identity, and J satisfies some integrability condition. So if we have J, then the complexified tangent bundle decomposes into the holomorphic vector, holomorphic tangent vectors, and anti-holomorphic tangent vectors. And this is the eigenspace associated with root -1. And this is the eigenspace associated with minus root minus 1. Then the integral condition means that the section of 1, 0 vector is closed under the Lie bracket. Then J is called a complex structure. Now, we assume J is omega compatible. Here, omega compatible means that omega satisfies this equation, and then we have the symmetric tensor Gj by using omega and j like this. This is symmetric two tensor. Then this symmetric two tensor is positive definite on every tangent space. In other words, Gj becomes a Riemannian metric on X. Then J is called omega compatible. If on projective manifold X and omega, if we have J, if the omega compatible complex structure J is given, then omega becomes a Kota form. The complex manifold Xj. J is a complex manifold induced by J. And then Kota form is 1-1 form Xj. So by since LH nabla is the prequantum line bundle, so F nabla is given by omega. So F nabla is also type 1-1. Then we can see that the pair of L and nabla is holomorphic line bundle. The holomorphic structure is given by the diva operator, which I denote by nabla diva j. This is a map from the smooth sections of L to zero-one form variable by this. Here, Z1 to Zn is a holomorphic coordinate. On the complex manifold Xj. So because J is integrable, so by Newland-Nielsenberg theorem, xj become complex manifold. So we can take holomorphic coordinates. Then we can define the vector space consists of the holomorphic sections of L, which are denoted by A0, xj, lj, and I put it vj. This is a space of the smoothness of L, such that lambda d by j is 0. So this means S is holomorphic. So this is the vector space of holomorphic sections. If X is closed manifold, then it is known that this vector space becomes finite dimensional. And its dimension can be computed by Riemann-Roch theorem. If the L tensor kx inverse is positive, kx means the canonical bound of x. So if the Kodaira vanishing theorem holds, then by Riemann-Roch theorem, we can compute dimension of Vj, and it is finite value. So this is the first example of the structure. So now I considered the complex structure. If the omega compatible complex structure is given, then we have the vector space Vj. Next, I consider Lagrangian fibration. So let mu be, so now I define mu, the map mu is called Lagrangian bundle. If B is a smooth manifold, dimension is n, which is half of the dimension of x. And mu is smooth surjective map that of d mu x is surjective for any x. So mu becomes submersion. Mu is a submersion. And moreover, mu is Lagrangian. So it means for every B, the inverse image of mu inverse B is Lagrangian submanifold. This notion has already appeared in the yesterday's Miranda's talk. The definition is the restriction of omega to the fiber mu inverse B then we call mu the Lagrangian fiber bundle. So in general, mu A has a critical value, but for the simplicity in this talk, I consider only the case of mu does not only the case of mu does not have critical value. So all of the elements in B are the regular value of mu. So we assume this condition, d mu x is always surjective. Moreover, we also suppose, assume in this talk that mu is proper. So every inverse image of compact set is also compact. And the inverse image of mu inverse B is every mu inverse B is connected. Then by using the action angle coordinate by the Liouville arc, we can check that, we can show that mu inverse B become mu inverse B is diffeomorphic to n-dimensional torus. Torus is the direct product of the circle. Now, we consider the sections S of L such that on every fiber of mu, if we restrict S to every fiber, then they are parallel. So S is parallel, so along every fiber. Now I define the Bohr-Sommerfeld fiber. Mu B is called a Bohr-Sommerfeld fiber, or we also call B is Bohr-Sommerfeld point. If there exists a non-trivial section of L restricting to the fiber mu inverse B, which is part of mu inverse B. Now let me explain the max. Now, since mu inverse B is Lagrangian, so the restriction of omega to every mu inverse B is vanishing. Then, since F nabla is equal to minus root minus 1 omega, then we can see that the pair of L and nabla restricted to the fiber, every fiber, is a flat line bundle. And moreover, we have found that mu is proper and mu is connected. So then mu inverse B is torus. In particular, mu inverse B is compact and connected. Then if the set of smooth section of L with mu inverse B, which is parallel.
Считаю, что я трогаю.
Sorry. Do you have any questions? Okay. Okay. So if the space of parallel sections on mu inverse B is non-zero, is non-trivial, then it is the dimension of this space is one dimension. So now I write this H0 L mu inverse P nabla mu inverse P. And this is the space of the fiber-wise, the parallel sections on the fiber. Then here, I V mu, the vector space, to be the complex vector space whose dimension is equal to the Bohr-Sommerfeld fibers. And this is the direct sum of H0 L mu inverse B nabla mu inverse B. This is not a precise definition of B mu. To define B mu more precisely, maybe there is sheaf theoretical definition of B mu, but maybe tomorrow's Miranda talk or after talk, it will be mentioned. Maybe it will be mentioned. So, but here in this talk, please let me define V mu to be the vector space whose dimension is equal to the number of Bohr-Sommerfeld fibers. Here, I should remark that the Bohr-Sommerfeld point, the set of Bohr-Sommerfeld points in B is discrete in B. So in particular, if B is compact, then Bohr-Sommerfeld fiber, the number of Bohr-Sommerfeld fiber is finite. So if B is compact, then V mu is vector space and dimension. Here, let me show an example. Let's be two-dimensional torus. And I wrote the element in T by E2 IX and E2 IY. And let omega is a symplectic form on T2 given by dx. And let L be a line bundle on X defined by this R2 times C over some Z2 action. Here, the action of Z2 is given by this form. Here, XY Z is in R2, and let M and N be integers. Then the action is given by X plus M and Y plus 2 pi N and exponential IMY times C. Then L becomes a complex line bundle on X. Next, I define the Hansha metric on L. This is standard. So sorry. Let P is in R2 or R. Then Hansha metric is given by Xi1 times Xi2 bar. Then this Hansha metric descends to L. And nabla is given by D minus square root of -1, the sum of, square root of -1 x dy. And then this connection descends to L. So first of all, we the nabla on the universal cover of L. So L2 we define these objects on R2 times C. This is a trivial line bundle. Then we can see that this descends to the. And we can check that the curvature form is given by minus square root of -1 omega. So L and H and nabla is a prequantum line bundle on X and omega. Now, the Lagrangian fiber bundle, which is a map from X to one-dimensional torus by the projection. Then all of the inverse image become Lagrangian submanifold. Then in this case, mu inverse E2 to pi ix is become Bohr-Sommerfeld fiber if and only if x is in integer. So E2 pi ix is equal to 1. So in this case, there are only one Bohr-Sommerfeld fiber. this is, I think this is a typical example of Bohr monomer fiber. Then in many cases, examples of symplectic manifold. In many examples of symplectic manifolds effectively with prequantum bundle, we can check that the dimension of Vj is equal to dimension of V mu if the both of J and mu is given. For example, it holds, this equation holds on Abelian variety. Or Frank manifold. The Frank manifold, this equation is given by Gurman and Sternberg. So in many examples, this equation can be observed. Now, let me explain. Let me explain the deeper relation between Vj and V mu. Now I explain. I direct the interpolation between V mu. Some examples. Following.
Sorry, can I just ask a question?
Yes, yes.
You said that there was a comparison between Vj and V mu. So you suppose that on X you have also a complex structure so that you can talk about these two structures simultaneously, or did I sleep all of your talk?
So for example, in these examples, so J and mu are given explicitly. So for such a concrete example of J and mu, you can check this equality.
Here you take the usual complex structure on the two torus.
Sorry, pardon?
Your J in the example is the usual or one of the usual.
Yes. In T2, yes, usual examples. So in this example, J plus ddx to dd. Sorry, maybe the coefficients may multiplied and ddy to minus ddx, the standard one.
Okay, thank you.
And in some examples, the following results are known. there exists a family of one parameter family complex structure such that J is converging to mu as 0. And the convergence of vector space VGS to D mu holds S to 0. I should say these two convergence more precisely. The first one is in the scope polarization. So we can treat the omega compatible complex structures and Lagrangian operations by the unified way, by the notion of polarization. And polarization is a sub-one P of the complexified tangent bundle, such that the restriction of omega x to every px is vanishing, and so px is Lagrangian on every x, and so is n, and p is relative. So the integrability holds. The section of P is closed under the Lie bracket. And this is the notion of polarization. If complex structure, omega compatible complex structure, then we can associate J with Pj, which is the anti-holomorphic vector bundle of X. So this is a sub-bundle of Tx tensor C. And if mu is a Lagrangian fibration, then we can associate mu with P mu, which is a kernel D mu tensor C. Then we write J is converging to mu the PJS converging to P mu as a section of Grassmannian bundle, as a section of Grassmannian bundle on X. So let me explain by example. This is the previous example. This is a previous example. Then define JS by the dx to 2 pi over s times y, and dy maps to minus s over 2 pi ddx, and positive real number. Then in this case, the anti-holomorphic tangent vector is by minus is over 2 pi ddx plus ddy. And this is the basis of anti-holomorphic tangent vector. And kernel d mu is spanned by dd. Then if you take S to 0, then this converges to this one. And let me remark that in this case, we have the Riemannian metric GJS by using omega and JS as this. Then this Riemannian metric is written as 2 pi s plus dx square plus s over t 2 pi dy square. Then this Riemannian metric, this family of Riemannian metrics means that so now we are considering two-dimensional torus, and this means that so we take s to 0. Then the radius of here is shrinking, and the radius of here is expanding if s goes to 0. So anyway, this is the convergence, meaning of the convergence of the polarization. And next I should explain the convergence, the second convergence, the convergence of this one, the vector space. So let me explain this convergence by this example. We can check that there exists in the homomorphic sections of LJS. And by the Riemann-Roch theorem, we can show that this is one-dimensional complex vector space. So it is generated by one vector. And phi s is the generator. And that we can take phi s such that phi s converge to delta in the which is the distributional sections of L. And delta is distributional section. Mu inverse 1. And mu inverse 1 is the unique Bohr-Sommerfeld fiber of the example. So, we regard this as a basis of B mu. So in general, the convergence of two asterisk means that we can take the basis of B phi S1, the phi Sn, and take the so B mu delta 1 delta, and these are the distributional sections, and every delta I is supported by every Bohr-Sommerfeld fiber, and n is the number of Bohr-Sommerfeld fibers. Then each of them converges to delta s to 0. this is the meaning of the convergence of the VJS to V mu. Then there are several examples such that this type of convergence holds. So there are several examples of the result that there exists a one parameter family of omega Convergence converging to mu such that the vector space VJS converging to V mu as is to 0 holds in the case of following. First one is abelian variety. This is an higher dimensional generalization of the above examples. And it is shown by there now nonetheless. And also shown by recently by Yoshida, Takahiko Yoshida. And it also holds on toric variety, smooth story by these people. And on flag variety, in the case of flag variety, it is shown by Hamilton and Kohn. Now, let me explain the aim of this talk. Give the conceptual explanation of the above results. So the type of theorem that exists such that VJS to V mu from the viewpoint of measured Gromov-Hausdorff convergence and convergence. And this is the aim of this talk. So this is the outline of my talk. First of all, shows VJS. This is the space vector. VJS is the space vector space of consists of holomorphic section of LJS, and shows that this space is identified with the eigenspace of Laplacian of some Riemannian metric G hat S. G hat S is some Riemannian metric defined on the unit sphere bundle of LH. This SLH is the unit circle bundle on L. So that the pair of this unit circle bundle and the Riemannian metric G hat S converges as S to 0 converges to some metric measure space. Then if the convergence of Riemannian manifolds is given, then the convergence of the Laplace operator also holds by spectral convergence result by Fukaya or Chiga-Colding. So show the spectral convergence the Laplacian given by G hat S as S to 0. And the limit. And this is the outline of my talk. So now it is time to stop. And tomorrow I have the second lecture on the morning, and in the afternoon I have one exercise session. In the exercise session, I will show some elementary examples of my talk, but I think it will not take so long time. So in the rest of the time, I would like to receive. I'd like to answer questions if you have questions. So I stop here today. Thank you.
Yes. Are there questions from the, yeah? Yeah, I've got one question. So if you consider toric varieties like, I think one of the simplest cases would be CPN, right? So you don't have Lagrangian fibrations without singularities, or do you? So what do
you are considering CPN? So are you considering CPN?
Yeah, so what would the Lagrangian fibration on CPN, for example, look like?
Yeah. So CPN is toric example of toric variety, and in the case of toric variety, the Lagrangian fibration, the Lagrangian fibration comes from the moment map always has a singular fiber, and so it is much more difficult. But I can show that the spectral convergence result in the case of also on the toric variety, but it is more complicated because the fibration has singularity, and moreover, in this talk, in this story, we use the convergence of the spectral convergence of spectral structures, and it is they are given by Fukaya or Chiga coding. And in the setting, we have to show that the lower bound of Ricci curvature. So we write G hat S, and we need the lower. We need that the Ricci curvature of G hat S has uniform lower bound. And in the case of toric variety, it is in general the uniform lower bound do not exist. So we need some more complicated argument.
Okay, thank you. Okay, so there was a remark by Eva Miranda that the singularities in this case are just elliptic, so easy to handle. So,
yes.
Any other questions?
Can you, so for the convergence, the first type of convergence, can you view this also as convergence of, say, a projection, so of some sort of map? And if so, which topology would you use? I'm interested.
So we convergence.
The first one.
First one. So it is so sorry. So this convergence. Yes. Yes. Roughly speaking, it is. It is enough. We have C2 convergence, but the precise yes, but the precise statement is rather complicated. So it is difficult to say here.
Okay.
Yeah.
Further questions? Okay, so thank you very much again for your talk.
Thank you.
And there will be the coffee break.